Hello again, everybody. We're getting towards the end of our chapter 5 on forces and Newton's laws, and we're working on some example problems dealing with connected objects. And these connected objects are actually in configurations that we call Atwood machines. And this machine, this pulley right here, is going to turn, it's going to spin one way or the other depending on where the net force is on that machine. Now we've got three masses right here that look kind of all the same size, but we can see that this one right here is much more massive than the sum of these two on this side right here. These two only add up to 12 on this side of the pulley. This one is 18, and so we can pretty much see that this pulley is going to rotate in the clockwise direction. And you know, while we're at it, why don't we just establish the clockwise direction to be positive and the counterclockwise direction to be negative. You don't have to. You can make them opposite if you want. But then that just means that we're going to say that the acceleration would have the opposite direction as well. But I think it makes sense for us to call this direction positive, and therefore we should have a positive acceleration. All right, so I'm going to take this slide right here, and on the slide we're going to find the acceleration of the system. Okay, the acceleration of the system. And then I'm going to shrink it down, and then we're going to find the tension in the cable. Now, the problem says tension in the cable. I'm going to say the tensions in the cables for the Atwood machine, because there should be a different tension between box 2 and, well, the 2 kilogram box and this one right here. You know, in fact, I should label the boxes 1, 2, and 3. Then this tension right here. We can't assume these tensions, this one and this one, to be the same. In fact, we're going to find that they're going to be different. Think of it like this. If you had a 10 kilogram box here and an 18 kilogram box, it would still accelerate counterclockwise, right? And there would be a certain tension between those two masses. They're both pretty massive, all right? So that tension would be a significant amount of tension. But what if you had, instead of a 2 kilogram box down here at the bottom, you had a, I don't know, a feather, something very, very, very unmassive, right? You could definitely see how the tension between that feather and the yellow box right here would be very different than the tension between these two boxes. So we can say that, all right, we can pretty much envision or predict that this tension and this tension is going to be different. I'm going to label these boxes before we go any further. Let's see if I can find a color that will stand out against all of them. How about light blue? All right, so I'm going to call this 1, call this 1 right here, call this 2, and call this one 3, all right? Mass 1, mass 2, and mass 3. Let's find the acceleration of the whole system, okay? So our statement about the net force of the system is going to be the mass of the system times the acceleration of the system. We can also say that the net force is a combination of all the forces, all the component forces, net force of the system, that are acting on that system. All right, so what are the forces that are acting on the system? Well, they're all weight forces, right? We have, I should be able to color code these, mass 1 times gravity, right? And that's acting in the positive direction, right? So see how it's acting kind of clockwise right here? So we're going to call that positive. But I'm not sure if yellow will show up. Let's use orange. Mass 2 times gravity, and mass 3 times gravity, M3G right here, they're going to be acting in the opposite direction. So we're going to have to make those assumptions. I'm going to put a minus sign and a minus sign right here in black and change my color. So mass 3 times gravity, that's going to be, oh, I'm sorry, not 3, mass 1. Mass 1 times gravity in the positive direction, and mass 2 times gravity and mass 3 times gravity are going to be in the negative direction because they're acting counterclockwise. All right? So Positive, negative, negative. All right, all these are going to be equal to the mass of the system times the acceleration of the system. So let's just go ahead and add them up. I'm going to do them on the right-hand side here. Mass, I'm just going to write all in black, I think now. Mass of the system times acceleration of the system equals mass 1 gravity minus mass 2 gravity minus mass 3 gravity. Okay? So the acceleration of the system we should be able to solve for now, right? m1g. By the way, let's simplify this a little bit. What do all these in the numerator, well, it's going to be in the numerator, but all of these right here added together have in common? They all have g, right? So let's factor g out and bring it out front. G times m1 minus m2 minus m3, okay? All over, we're dividing by the mass of the system, right? It's coming down the bottom right here. So, that's funny, that's mass 1 plus mass 2 plus mass 3. All right, let's find the acceleration of the system. I'm going to move this over. I'm going to have to. I'm going to see because I'm going to run out of space. Acceleration of the system is going to be 9.81 meters per second squared, of course, times a quantity. Mass 1, that's 18, right? 18 kilograms minus 10 kilograms minus 2 kilograms, because they're acting in the opposite direction as the 18, all divided by 18 plus 10 plus 2. That's the whole system. So you can see that even though the forces are acting against each other, and so whatever the difference between 18, 10, and 2 is, that's the force, that's the mass that's acting with gravity to create the force, but it's still, you've got to use that force to pull the whole system, which is the sum of all those together. Okay? So, 9.81 times the quantity 18 minus 10 minus 2. I'm going to take that and divide that by the quantity 18 plus 10 plus 2. Did I get that right? I think I did. I get an acceleration. That means the acceleration of the system, I'll write this out again, is going to be 1.96 meters per second squared. And I didn't put a negative in front of it, so it's going to be positive. It's going to be in the positive direction, which is what we predicted from the very outset. Okay? It's going to be going, if you want to say it, clockwise, in the clockwise direction. That's positive, counterclockwise is negative. Okay, so having done all that, having found the acceleration of the whole system, which is what we just did right here, that's kind of like part A. Now I'm going to look at cable, I'm going to call that, let's see, let's make this, what color should we make this? Make this green, all right. I'm going to call that tension 1, 2, and I'm going to make another tension down here. Let's make it, oh, I don't know, green, well, no. I'm killing myself picking colors right here. Hopefully there aren't too many colors. Call this tension 2, 3, like that. All right, I made them do different colors because they're going to be different tensions, and we're going to solve what they are right now. All right, but it's important to solve for what they are. But what is important to solve for them is knowing the acceleration of the system. Because, again, our assumption is the acceleration of the system is the acceleration of any one of these boxes. And we're going to look at these boxes individually to find out what the tension on that box is. All right? So, let's take all this and just shrink it down. All right? I'm going to take this whole thing and just... see, lock rotation. I don't want my whole thing to move right here. Sorry about that, I'm being extra picky. All right, let's just do this. All right? So let's find the tension of 1 to 2. That's the green one, all right? For T1, 2. Now what we can do here is that we can look at either box 1 or box 2 because they both have that tension attached to them, right? The tension in the rope is attached to box 1 and box 2. But all we have to do is look at only one of them because the same tension is going to be attached to the other box right there. All right. So for tension box 1 to box 2, what might be easier to look at? I think it'll probably be easier to look at box 1 because it's only got one thing attached to it. All right. It's only got this tension upwards, T1, 2, that we're solving for right there. So let's look at box 1. Box 1. What kind of net force statement can we make about box 1? Net force on box 1 is going to be equal to mass of box 1 times the acceleration of box 1. And by the way, we know the acceleration of box 1 because that's the acceleration of the whole system, right? But just as true is the net force on box 1 equals the sum of all the forces acting on box 1. What's one force acting on box 1? Well, the force of gravity, right? The weight force. We call that M1G. What's the other force acting on box 1? The tension force. Now, we know box 1 is sinking down because it's the most massive. It's going to be going down like this, but it's not going to be dropping like a rock because of gravity because, first of all, we know that because the acceleration of the whole system right here is only 1.96 meters per second, only a fraction of gravity. And that's caused because of this tension force, tension with the other boxes, kind of holding it back, all right? So that tension force is what is acting against box 1's gravity, T1, 2. And by the way, that's what we're solving for right there. So it's handy to have that. So which one is the positive direction? Well, we were saying that the clockwise direction is positive. So why don't we go ahead and write that one first, M1G. All right, and so that means the counterclockwise direction is going to be negative. So that means our tension 1, 2, is going to be acting in the negative direction. All right, at least as far as box 1 is concerned. Okay? It's the tension is, you might say, holding back box 1 from falling faster. Well, let's set these all equal to each other. All right? M1G, I'm going to stay with black now. M1G minus tension from 1 to 2 equals mass of 1 times the acceleration of 1, which is the acceleration of the whole system, right? It's good that we know this right here, 1.96 meters per second squared. All right, so let's solve for tension, and we'll have that for tension 1, 2. So tension 1 to 2, I'm going to take this and I don't really like the fact that it's a negative right here, so I'm going to add it to this side, all right, and then I'm going to subtract M1A1 to this side right here. Everybody see what I'm doing? All right, so tension between 1 and 2 is going to be M1G minus mass 1 times acceleration of 1. Let's just factor out our M1, and so that's going to be gravity minus the acceleration of 1 right there. Okay, let's plug in our values. Mass of 1 is 18 kilograms times the quantity 9.81, that's gravity, minus 1.96. You know, I haven't been putting my units in like I should, and I should at least keep it consistent. So, what does that add up to? What is a tension between box 1 and box 2? You might see the green one. In fact, I kind of strayed away from my green notation right there, but I'll box it in green. 18 times a quantity 9.81 minus 1.96. I get 141 newtons. 141 newtons. And that's going to be our tension between box 1 and box 2. Like so. All right, now let's solve for tension between 2 and 3. For tension 2, 3. Now hopefully I'll be able to do this a little more expediently because I sort of laid it out in a little more detail up here. Now look at box 2. Box 2 has got this tension pulling up. We can use this if we want because we just solved for it right there. This tension is pulling it upwards. It's also got tension between 2 and 3 pulling downwards. We can look at box 2, but it might be simpler just to look at box 3 because box 3 only has tension pulling up and then, of course, the weight force pulling down. So let's look at box 3. Box 3. In fact, it's right next to us right there. All right? We've got M3G pulling down. That's going to be in the negative direction, right? Because counterclockwise is the negative direction. We've got tension between 2 and 3. Tension 2, 3 pulling upwards, and that's going to be the positive direction. All right? So first thing we can say about box 3, net force on box 3, equals the mass of box 3 times the acceleration of box 3. And of course, we know the acceleration of box 3 because that's the acceleration of the entire system. We also can state the net force on box 3 as being the sum of the forces. Tension 2-3 is going to be in the positive direction. The M3G is going to be in the negative direction because it's acting against the direction of motion. So that's going to be T2-3, right? Tension between 2 and 3, which is what we're solving for right here. You know what? I should leave that purple for the time being just so you can sort of pick it out. T2-3 minus M3G. Mass of 3 times gravity. That's the weight force of mass 3 right there. All right, let's set them equal to each other. Now I'm going to use just black. T between 2 and 3 minus mass of 3 times gravity equals mass of 3 times the acceleration of 3. Let's just solve for our T. Tension between 2 and, keep writing 2, don't I? Tension between 2 and 3. I'm going to add over my M3G, right? So that's M3A3 plus M3G equals, oh, that was my dog barking upstairs. You can hear him. M3, I'm going to bring that to the, I'm going to factor that out. Mass 3 times the sum of acceleration 3 plus G. Just barely have enough space. What's the mass of 3? It's only 2 kilograms, right? 2 kilograms times the sum of acceleration of 3. What's the acceleration of 3? It's the acceleration of the whole system, right? That's that 1.96. 1.96 plus 9.81 meters per second squared. And 2 times the sum of 1.96 plus 9.81. I get 23.5. 23.5 newtons. I'm going to circle that in purple because that was our tension between 2 and 3. And that is clearly a different tension in this string than it is in the green string right here, the green cable. All right? So that's our setup for solving what tension forces are between any two boxes. We solve for the acceleration first, and then we look at each individual box and use that acceleration and apply it to that box to find the forces that are on it. All right? Thanks for following along. That was quite a long one, but I think it's worth it, and we'll do one more video segment after this. But I appreciate your patience if you stuck in with me there. So again, thanks again, and make sure you come to me if you have any questions. I'll see you on the next one.